In this video, we're going to look at transforming exponential functions, and we're going to do this using a program called Desmos. Desmos is a great graphing tool, and it's really useful when you want to quickly create graphs and compare them as well. In this video, we're going to look at three types of transformations that we can perform on any exponential graph. The first one being changing the steepness of the graph. Our second transformation is known as a translation. Translations are where you move your graph either to the left, the right, or up or down. Our third transformation is called a reflection. We're going to learn how to reflect a graph over either the x or the y-axis. Now I need to point out that the transformations we're looking at in this video are based on the basic exponential function y equals a to the power of x. Some of the properties that I teach you in this video will not actually apply to more complex exponential functions. But you don't really need to worry about that, since the Standard Mathematics course does not really delve into complex functions. So we'll start our video by talking about our first transformation. We'll talk about changing the steepness of our graph. Now up above you will see that we have our basic exponential equation y equals a to the power of x. A is usually some sort of a number. So what I'm going to do is I'm going to bring up Desmos now, and let's type in y equals 2 to the power of x. 2 to the power of x is a very common and basic exponential. When we think of exponentials, we think of a graph that looks similar to the one we see here. But as I mentioned, we can perform some transformations here and make it look a little different. So going back to our PowerPoint, it says, what happens when a equals 1? And we're going to explore that first. So instead of 2 to the power of x, this time we're going to do 1 to the power of x. You might have noticed I didn't write y equals 1 to the power of x. In Desmos, you don't have to do that every time. So I'm just saving myself a bit of time and not writing y equals. Now you'll notice that 1 to the power of x makes a straight line. It doesn't look like an exponential at all. And in fact, it's not. So we'll go back to our slide here, and we'll make a little note to ourselves. When a equals 1, meaning we've got y equals 1 to the power of x, it makes a straight line. And we need to remember that y equals 1 to the power of x is not an exponential. Exponentials cannot be a straight line. So let's look at our next question here. It says, what happens as a increases in magnitude? I've picked a value of 1 instead of a, which gave me the straight line. And I've already picked a value of 2 instead of a, which gave me a really basic exponential function. I'm interested to see what happens if I pick a number somewhere between 1 and 2. Let's go with 1.5 to the power of x. And you'll notice that we get this purple graph here, which is partway between the red and the green graph. Alright, so if I picked a number smaller than 1.5, should it be partway between the green and the purple graph then? Let's try that. Let's try 1.2 to the power of x. That gives us our black graph here. I'm noticing that as my numbers get bigger than 1, the graphs seem to get steeper and steeper. So far, 2 is the biggest number I've used, and it's the steepest graph. So what's going to happen if I try a number bigger than 2? Let's try 5 to the power of x. And you can see we've gone steeper again. I'm really curious now about how steep I can go. What's going to happen if I pick a number that's really, really, really big? Let's try this number here to the power of x. When we look at this graph this time, it's become so steep that it almost looks like a right angle. It's not, but it looks like one. While we're looking at all these graphs, I want to point out some things that we looked at in an earlier video. First of all, you'll see that they all pass through the point 0, 1. All of them. It doesn't matter what value of a you put in, they still all pass through this point. The second thing I want to talk about is, well, let's look at what happens when I zoom out. If we look at the graphs, do they ever go below the x-axis? And the answer is no. No matter how far I zoom out, they will never go below the x-axis. In fact, they don't even touch the x-axis. The graphs will get very close to the x-axis, but they never touch it and they never cross over it. So if we go back to our slide, you'll notice I had an image of these graphs all along as a bit of a note to look at. And we can see that as the value of a increases, the steepness of the graph increases. So I'm going to write a little note here. As a increases in magnitude, the steepness of the graph increases. The next question we're going to look at is what happens when a is between 0 and 1. So bringing up Desmos again, here we've got y equals 2 to the power of x, which is a really basic exponential function. So I'm going to pick a value of a between 0 and 1. That's normally like a decimal. So y equals 0.5, let's say, to the power of x. 0.5 is a number between 0 and 1. It's halfway between them, in fact. And you'll notice that we get a graph that's a bit different. This time, rather than starting off flat and then increasing rapidly, we start off quite steep, coming down and then flattening out later on. This opens up a really great discussion about exponential growth and also exponential decay. The graph we see in red, y equals 2 to the power of x, is an example of exponential growth, where at first something seems to be not changing at all, and eventually it starts to accelerate and things seem to go up very quickly. A perfect example of this is the coronavirus. When countries don't put restrictions into place, the coronavirus seems to spread, as they say, exponentially, or to grow exponentially. That's why we call this exponential growth. The purple graph is a great example of exponential decay. Once countries put restrictions in place and the number of coronavirus cases seem to peak, eventually they would decay exponentially. And we can see this on our graph for Australia. These are the number of daily new cases of the coronavirus. You can see it seems to grow exponentially, and then once the restrictions are in place and it has peaked, eventually it will decay exponentially. You'll notice that the curve seems to flatten out as we get to the right, but it never seems to reach 0, which is a perfect example for our exponential graph. We know that as we come down here to the right, it seems to flatten out, but it never touches the x-axis. It never goes below it, for sure, as well. You can't have a negative number of people with the coronavirus, right? So once again, if I zoom out, you'll notice that this graph never ever touches the x-axis. Now, I'd like to explore what happens if we put some other decimals in. Some things other than 0.5. Let's try 0.9 to the power of x. And what we notice is that it's quite flat, this curve. Much flatter than the one that had an a value of 0.5. And one thing you'll notice is that as you approach 1, your curve will become flatter each time. Why is that? Well, you might remember that if it was 1, if it was 1 to the power of x, it would be completely flat, because 1 to the power of x makes a perfect straight line. So the closer I get to 1, the flatter you'll find your curve, right? So if I do y equals, let's say, 0.99 to the power of x, it starts to look really flat. And if I zoom out, you'll see that eventually it does curve up. And the more 9s I put in here, the flatter the curve starts to get. Let's go back to where we were before. Alright, so we've learned that as our decimal gets closer and closer to 1, our curve gets flatter. What about if we have decimals less than 0.5? Decimals that are approaching 0. Let's try 0.4 to the power of x. And you'll see that we get a curve that's steeper now. So as our decimals get smaller and smaller and closer to 0, the curves get steeper. All right, so let's try one really close to 0. Let's try 0.1 to the power of x. And here we've got our steepest graph yet. If I pick a value that is almost 0, let's pick a really small number, this one here, and put this to the power of x. What are we going to get? We get a graph that is so steep, it almost looks like a right angle. Now, while we've got these graphs up, I'd like to point out once again that they all pass through the point 0, 1. And this has been a common theme that we've seen here. The other thing, as we mentioned before, is if we zoom out, we notice that the graphs never go below the x-axis and they never touch it either. So we need to write some notes here. Probably the first thing we noticed was that our graphs represented exponential decay. The other thing I noticed was when a approached 0, for example, where we had 0.1 or even a smaller number than that, we noticed that our graph got steeper. Finally, what happens when a approaches 1? For example, where we had 0.9 to the power of x, having a number that's almost 1, you start noticing the graph becoming flatter, or the curve becoming flatter. If I had 0.99 to the power of x, it'll become flatter again. This didn't just happen for numbers between 0 and 1. This also happened for numbers that were greater than 1. For example, if we look above, here we have a number that's close to 1, 1.2 to the power of x. It's almost 1, and you start noticing the curve becoming flatter. So if I picked 1.1 to the power of x, it would probably become flatter again. So whether the number that is approaching 1 is less than 1, such as 0.9, or more than 1, such as 1.2, we start noticing that curve becoming flatter, almost becoming a straight line sometimes. Now I'm going to segue back to the COVID-19 outbreak that we seem to talk a lot about. You might have heard that we've got a thing called a growth factor, and we've been told that in order to keep the coronavirus under control, we've got to keep the growth factor below 1.0. Now, if we look at this diagram here, currently June 7th, it was at 0.94, which is in the green. That's a good thing. Whenever it was in the red, it had gone above 1. That's when it's dangerous. That's when the coronavirus is starting to get out of control. Now, if you think about that and go back to Desmos, you might remember that when the number is less than 1, for example 0.94 to the power of x, you get exponential decay. What happens when the number is above 1? Going back here, the highest it's ever been is 1.28. What's going to happen then? Well, when it's above 1, you might remember that we get exponential growth. And if we also think about when it equals 1 to the power of x, it made a straight line. So 1 represents no growth as well as no decay. Numbers above 1 represent growth, and numbers below 1 represent decay. This is why we have been told that our growth factor has to always be below 1 if we hope to get rid of the coronavirus. Now, before we move on to the next transformation, let's write a couple of notes to ourselves. First of all, we know that they all seem to pass through 0, 1, or 0, 1. And I'm going to draw kind of like an imaginary line across my x-axis. And I mentioned this in an earlier video. This imaginary line is known as the asymptote. A-S-Y-M-P-T-O-T-E, the asymptote. And an asymptote is basically an imaginary line that the graphs never touch nor go below. So I'm going to put an asymptote line on our graph below. All right, let's move on to our next transformation. This is called a translation, and this is all about moving the graph left, right, up, or down. So we'll bring up Desmos, and I have a very basic exponential function, y equals 2 to the power of x. Let's say I just want to move this up 4 places. It's really easy. All I need to do is copy down the exact same equation and just add 4 at the end of it. You'll notice that our new graph, the blue one, is just 4 places above the red one. You might also notice that it doesn't pass through 0, 1 this time. That is because if you take the point 0, 1 and move it up 1, 2, 3, 4 places, it is now 0, 5. What if I want to move the graph down? How would I do that? Some of you might have guessed already. If I want to move it down 3 places, I just subtract 3 at the end. So up-down translations are really easy to perform. So we'll write a little note on our slide. Here's an image of what we just did. And I'm going to say that you just need to add a number at the end of the equation to move it up, or subtract a number to move the graph down. Now we need to look at right-left movements. Once again, we just copy the same equation. I'm going to put my x here in brackets, and I'm going to subtract 3 next to it. And what you'll notice is when you subtract 3, it moves the graph 3 places to the right. So how would I move the graph to the left? Let's say I want to move it 4 places to the left. Some of you might have already guessed how to do this. Once again, we put it in brackets, but this time we're going to add 4, which will move the graph 4 places to the left. Now this can be a little confusing sometimes because it seems to be the opposite of what you think it would be. Subtracting, you would think, would move it to the left, and adding, you would think, would move it to the right. But it's actually the opposite of what you think it should be. Subtracting moves it to the right, and adding moves it to the left. So let's write a little note to ourselves again. Here's an image of what we've done. So I've written down subtracting x by a number moves our graph to the right. Adding a number to x moves our graph to the left. And remember that we need to put x in brackets when we do this. If you don't, this can cause some errors later on. We need to reflect back on our translations that moved our graph up and down. You might have noticed that our asymptotes changed in this situation. For example, here's one here. This dotted line is a new asymptote for my graph y equals 2 to the power of x plus 4. The graph y equals 2 to the power of x plus 4 never goes below the point at which y equals 4. You might have noticed we've got a new asymptote for our red graph. This imaginary line is our asymptote, and our red graph never ever goes below it nor touches it. When we originally spoke about exponential functions, we talked about how the asymptote always seems to be on top of the x-axis, And we also said that the curves always seem to pass through the point 0, 1. But as soon as we performed some translations here, we started seeing the asymptote changing positions, as well as this point at which the graph passes the y-axis. It doesn't seem to pass through 0, 1 anymore. The last transformation we're going to talk about is known as a reflection. And we're going to talk about reflecting the graph over the x or the y-axis. So we'll bring Desmos up, and we're going to copy the exact same equation, and we're going to change it somehow. All I'm going to do is put a negative in front of my x. And you'll see that our new blue graph is a reflection of the red graph over the y-axis. So putting a negative in front of x will cause this reflection. In fact, let's do it for a different graph. Let's do 1.5 to the power of x. And let's take the exact same equation and put a negative in front of the x. And you'll see that our purple graph is a perfect reflection of the green graph over the y-axis. Some of you might have noticed that there's actually another way that you can reflect this graph over the y-axis. So we'll go back to y equals 2 to the power of x. And if I do y equals 0.5 to the power of x, you'll notice that we get a reflection this way as well. In fact, if I do y equals 2 to the power of negative x, again, you'll notice that our green graph is exactly the same as the black graph. It went over the top of it. So 2 to the power of negative x and 0.5 to the power of x actually give you the same graph. So if you ever want to model exponential decay, you can either use an a value between 0 and 1, or if your a value is more than 1, you can just put a negative in front of the x. Anyway, let's write a little note to ourselves about this. Here's a picture of our two graphs. I'm going to say that putting a negative in front of the x reflects the graph over the y-axis. Here we can see our original equation, and then our new equation that's been reflected over the y-axis has a negative in front of x. Now I'm not going to mention anything about how you can pick a value such as 0.5 to the power of x, because it starts getting a bit complicated then. We'll just try and keep this simple for now. We're also going to talk about reflecting our graph over the x-axis. How would I do that? Well, once again, I take the exact same equation, and this time I'm going to put a minus sign in front of the 2. And we can see that it's reflected our red graph over the x-axis this time. So here is a picture of what we just did, and we'll write a note to ourselves once again. We'll say that putting a minus sign in front of a reflects our graph over the x-axis. Here's our original equation, 2 to the power of x, and then we put a minus sign in front of the 2, which is our a value. Anyway, that concludes our video just looking at all the different transformations we can do with exponential functions. Remember to read the description below for links to workbooklets that relate to this video.